So our first plenary talk will be given by Professor Higham of the University of Edinburgh. Professor Higham is a professor in the field of numerical analysis at the University of Edinburgh. He's a recipient of various fellowships, awards, and prizes, including the Fellow of the Royal Society of Edinburgh. He has a broad experience, including the design evaluation of computational methods and stochastic computation, and he's the author of several books and peer-reviewed journals. Today, he will be giving a talk titled An Applied Mathematician Looks at Deep Learning. Professor Higham, it is a pleasure to have you here today. The floor is yours.
Well, thank you, Stavros. Let me share my screen. Could you confirm, Stavros, that this is sharing?
Yes, I can confirm.
And if I page down, is that working?
Yes.
Yes, okay. I'll go to full screen mode. So thank you for that introduction. It's a pleasure for me to join in with this activity. And we've been given the remit of addressing a wide audience, and I believe that there's a very wide range of people participating. So I'm trying to make this accessible. And we're meant to pick a topic which we think is fascinating and of interest to that type of audience. So that's what I intended to do here. And I picked the topic of deep learning. Stavros says my background is in numerical analysis and computational mathematics. So I'm going to be presenting this material from that background. So that's my perspective on these ideas.
Hi, Des. Sorry, can I just interrupt?
Yep.
I don't think the full screen worked, so we don't see it full screen, and we can currently.
Right. Okay. Let me.
Second slide.
Let me try again.
Yeah, it's still.
Yep. If I go to maybe try it this way. Is that better, Aretha?
It's still not showing in full screen. So
I believe the problem is that if you only share the window, when you go full screen, you cannot see it.
Right. Okay, so I didn't do the right kind of share. I'll try. If I unshare.
I think you have to share your full screen.
Yeah,
right.
Yeah, precisely.
Is that one of these options?
Yeah, it says desktop.
Yep, that one there.
Yeah, so that would show your whole desktop.
Right. Is that better?
Yeah, now we see it full screen, I believe, right? Or
I think so, yeah. It's full screen, but it's the third slide. Yeah.
Right, great. Okay, right. Apologies for that mess up. So these are my take-home points. So it's always good to start with take-home points, I think. So these are the reasons why I think this is a good topic for me to share with you. Deep learning clearly is currently a very active area, but it uses many of the ideas that we're familiar with in the world of mathematics and statistics. So we already know some of the stuff that's going in to these deep learning tools. In particular, for those of us teaching maths and stats students, we can make this very clearly when we're presenting even basic material, things like the chain rule, linear algebra, ideas in optimization. You know, we should be making it clear to our students, I think, that these are some of the building blocks which are used in many applications, including these new deep learning tools. So therefore, people that study these topics have a useful set of skills that make them employable in this field. Moreover, there are still lots of open questions in this area, and many of them can be addressed by people from the mathematical sciences. So I think it's a great source of research questions for mathematicians and statisticians to look at. And my third point, which is really part of point 3 again, is that even if you're not such a big fan of deep learning, maybe you think it's slightly overhyped, maybe you think it won't be such a big deal in a few years' time. Well, deep learning is part of a much bigger field of data science. And in my opinion, data science is not going to go away anytime soon. There's going to be more demand for people who know how to handle data and how to take actionable, make actionable predictions from data. So I think this general topic is something that we can be confident about contributing to, which will have lots of opportunities in the future. So I think these are good reasons for us to want to join in with these activities. I'm not going to even try to define what I mean by deep learning. What I've given here are some references, in particular, a couple of talks there at the bottom of the page. These are from recent conferences. You can find them on YouTube just by typing in these details. So Carola gave a public lecture at a conference over the summer, and Jan LeCun gave a more research level overview of the current state of the art and also his predictions for what might be the next big things in this area. The picture at the top there is taken from this introductory paper that I co-authored. This shows one of the classical image classification tools using a deep learning network. So here on the left, we input an image. So that's red, green, and blue pixels. That image, which is the input data, goes through various mathematical operations, and the network gives us a prediction. And hopefully it will predict that what we're seeing here, out of many different classes, we're hoping it will predict that that's a dog. So just for those that haven't got any experience of what deep learning networks look like, I'm going to give a very simple example. So suppose we have this as our input data. We have points in 2 dimensions, and some of these are red circles and some of them are blue crosses. So imagine, for instance, that this is a map and these are drill sites, and the red circles correspond to places where we've successfully found what we want to find underground, and the blue crosses indicate that at those drill sites we didn't have any success. So if somebody gives us a new point, we'd like to predict whether that's going to be successful or not if we drill there. Okay, so we want a function which takes points in the unit square and returns a prediction of whether this point belongs to the red circle category or to the blue square category. And of course, there are many ways you could split up the unit square, which gives 2 categories or 2 regions, one of which contains all the red circles and one which contains all the blue squares. Here's how it would happen from a deep learning perspective. So I'm going to look for a function, capital F, which takes these 2-dimensional points, x1 and x2, and returns a pair of numbers. And if the first component of the output is the biggest, then we'll say that that point is in category A. And if the first component is smaller than the second, then we'll say that that input point is in category B. So that's our classification function. And we're going to do this by alternating between linear and nonlinear transformations. And the nonlinear transformations that we do in this case will be using the sigmoid function, which I'm calling sigma, which has this simple form. And this can be motivated, at least somewhat heuristically, from a biological perspective. If you think of neurons in the brain, if they receive enough input, then they will fire, and if they don't receive enough input, then they won't fire. And this function here, which is plotted, if it doesn't get very much, if it gets a negative input, then it doesn't give you a large output, and then as soon as you cross over the origin, it starts to give you a large output. So it's a smoothed out version of something which either fires or doesn't fire, depending on the level of input given to it. There's going to be a bit more math notation coming up, and in particular, when I apply this function sigma to a vector x, what I mean is you'd simply apply the function to each component individually. So if x is a vector, sigma of x is a vector, and its ith component is simply sigma applied to the ith component of that vector x. So that's my style of notation. So here's the sequence of operations that would happen in the basic feed-forward neural network. So I'm going to build up this function f a bit at a time. So first of all, we have the input x, which gets multiplied by a matrix, and then a vector is added. So this is a linear or affine transformation. I'm going to put a bracket around that and apply my nonlinear transformation. So here's my neuron type nonlinearity applied to that vector. I then do a linear transformation of that. So multiply by a matrix and add on this extra vector called the bias. Then put that through the nonlinearity, and then apply a matrix and add a vector to that. And then finally, we're going to do another nonlinearity. So that's what I mean by applying a sequence of linear and nonlinear transformations. Here's the corresponding picture, which also tells you about the dimensions. So the input has these two components, the x1 and x2 coordinates. They get sent to these two neurons, and linear combinations of these are input to the two neurons. That's what W2 and beta are doing. The neurons then apply the nonlinearity. They output to the next layer, and these are linearly combined using W3 and B3, and they get sent to the next layer, and so on. So each of these dots is a neuron which applies its nonlinearity and then sends its information out to the next layer. And the final pair of points that we get are the output from that network. So I haven't told you yet what these matrices are. Our job is to choose those. They're called the weights and the biases. And we want to choose those weights and biases to respect the data that we know, to try to give us an accurate result on the training data. So those crosses and circles from the picture are what we used to choose these parameters. In fact, there are 23 numbers contained in these vectors and matrices. So more precisely, let's suppose these points are labeled in this way. So the crosses will be given a 0, 1 label, and the circles given a 1, 0 label. So if I go back to that initial picture, when we give it a red circle data point, we want it to give us a 1, 0, and when we give it a blue cross data point, we want the function to return a 0, 1. So that's how we're going to measure success on the training data. So these labels are now defined. So we introduce what's called a cost function. We might call it the error function or the objective function in optimization. So this is found by going over all the data points that we're training with and seeing how well our map does at reproducing the labels. So for all the circles, how well does it do at reproducing 1, 0? And for all the crosses, how well does it do at reproducing 0, 1? And here I'm taking the Euclidean norm and squaring. There are many other things you could do in terms of defining your cost function, but I think this is the most natural from the applied maths point of view. So that sets up this function f. It depends on 23 parameters, and we can try to choose those parameters to minimize this cost function. That's an optimization problem. And if I give that to MATLAB, which is a standard computing package, then it finds what it believes to be the solution to that problem. And what I'm showing here, based on that trained network, so based on the matrices and vectors that have come out, I'm showing a gray area, which is where MATLAB, the solution I got, would classify points as being members of the red circle category, and the unshaded area shows all the points where we would regard that point as being a member of the blue square category. Okay, so what I'm showing here is the boundary between those two categories. Now, as I said, there are many other ways you can think of to find a function which puts the red circles together and the blue squares together. So what's the big deal about this rather sophisticated looking combination of linearity and non-linearity? Well, the best thing I can say is it just seems to work. So what I'm showing here are examples of some of the game-changing deep learning networks that were developed. The example I showed there had 23 parameters in those weight matrices and the bias vectors. These deep learning networks that I'm listing here, they have millions of parameters. So AlexNet was perhaps the first of the groundbreaking tools of this nature. This has 60 million parameters for you to find. So you've set up this nonlinear function with 60 million things that you've got to fit to data. That's a pretty large optimization problem that you've got to solve, but you can tackle it, and the solutions that people get do seem to be successful. And in many areas, including things like speech recognition, image classification, language translation, board games, the deep learning approach does seem to give the best answers, the best tools for making these AI-type predictions. But anybody who's studied optimization will realize these are difficult problems. Training networks is not a simple task. It's a huge dimensional space that you're searching over. The optimization problem is not convex, so it's very difficult to prove anything about the solutions that come out of your numerical algorithms. So there's lots of stuff here to think about. I wanted to give a slightly bigger example. Here I'm using MATLAB's toolbox on deep learning, which I find quite straightforward to use. Of course, there are many other tools available these days. Some of these examples from the previous slide require quite sophisticated hardware. You need high performance computing style hardware to get those results. The example I'm giving here can be done on a laptop. So this is the MNIST data set, which is a very standard training set available online. It consists of handwritten digits. So people have written digits from 0 to 9 by hand. They've been scanned in and they're available now. So this is labeled data, and you can ask your system to learn to recognize those digits. They're fairly low resolution. These are 28 by 28 pixels. So that's 784 pixels. It's grayscale, so they're just black and white images. So I took a standard architecture with 15 layers and I trained on 7,500 images, and on the remaining 2,500, which the network hasn't seen, it was around 99% accurate, which is pretty typical of good quality networks these days. And you can see these are very low resolution, and in some cases it's somewhat ambiguous what these digits are. So the 1% error, it isn't necessarily even an error. It's just that the person who drew the digit may not have actually done a very good job of trying to reproduce the digit they were looking for. Okay, so I wanted just to emphasize that what we've done there is to build a function. So it takes a vector with 784 numbers in it. So this dimension 784 is the input. Those are all the pixels. It returns an output with 10 components. So it's a map from R784 to R10. It's a nonlinear function. And for example, you can look at the Jacobian of that function. And the Jacobian would tell you how sensitive the function is at that particular point to changes in the input. So for this input point here, which represents the digit 9, I'm showing the Jacobian. So there are 784 components in the input, and there are 10 components in the output corresponding to the 10 digits. So you can differentiate each of those 10 components of f with respect to any of those 784 parameters. So I'm putting all those partial derivatives into a matrix, and I'm showing you row by row how those partial derivatives behave. And this is intuitively reasonable. The number 9 here is a bit like a 0 and a bit like a 3. So those particular components of the output are quite interested in this number in the sense that they would change relatively significantly if you changed that data slightly. And of course the number 9 lights up, and the number 8 is a bit like a 9. So number 8 also seems to have some sensitivity there. So this is telling me how much the output function would change if I made a small perturbation in all the various partial derivative possibilities. Okay, and we're going to return to this topic very shortly. So these are some of the questions you might want to ask. Of course, the obvious question is, does this work? So does my trained network correctly classify new data that it hasn't seen before? That's a hard question to answer, and there's no way you can answer that unless you start making assumptions. You have to know something about the relationship between the data that you've trained on and the new data on which you're now judging your classification tool. But of course, there are people working on those questions. From my perspective as a numerical analyst, I'm also interested in how sensitive this mapping is. Have we built something stable? If we perturb the input, or if we perturb the weights and the biases that we've computed, how does that affect the map that we've produced? Also, a lot of these computations nowadays are done on relatively low accuracy hardware. There are some very fast but low accuracy units that you can produce, that you can use them based on some of the gaming hardware that's been invented in recent years. So in some cases, you're computing, for example, to about 3 digits of accuracy, and yet you're doing millions and millions of floating point operations, adding, subtracting, multiplying, dividing, millions of times, in each case only to 3 or 4 digits accuracy. So what can you possibly say about the accuracy of the overall solution? How do those errors accumulate? And for those that have studied numerical analysis or linear algebra and looked at errors, there are various ways you could try to prove things. So for example, you could take a backward error viewpoint and you could say, does my computed prediction correspond to the exact prediction for a nearby data point? If you could prove that, then that would be a great way to justify the use of these low accuracy floating point tools. Or maybe your computed answer corresponds to the exact answer for a nearby set of weights and edges. So these are the kinds of questions that interest me, and they're built on the concepts that we know from my background in numerical analysis. But I'm going to focus on one particular topic, which is really those 2 blue questions in the middle there. How sensitive is F? And this motivates an area called adversarial attacks. And here's a picture that you'll see in many presentations in this area. This really illustrates the idea. So we're starting off here with a picture, and this sophisticated deep learning tool, given that picture, will classify it as a panda. That's the most likely classification. It's almost 60% confident that that's a panda. But we can then make a small perturbation to that image. So we're adding these 2 images together, adding the pixels. And here's on the right is the resulting image. And because this is small, there's a 0.007 here, we haven't really changed the picture as far as the human eye is concerned. But this is a very specially chosen perturbation, and with this perturbation, if you give the picture on the right-hand side to this deep learning tool, then it will come up with the classification of Gibbon with 99% confidence. So by adding a specially chosen but almost visually imperceptible perturbation to that image, we've caused the classifier to change its mind and do something which from our perspective is completely unrealistic. So that's an adversarial example. Here are a couple of the classic papers in this area, in case you want to follow up on this. There's a couple more, because this is quite good fun doing these things. So here's a couple more from the web. This is an image which initially is picked out as in the category suit. We then add something relatively small to get this new image, and is now in a different category. This has been taken further, and it's possible to print out on a piece of paper a particular set of colors. And if you wear these, then video surveillance technology doesn't think you're a human anymore. So you can disguise yourself by printing out one of these patches and holding it up to the camera. That's a pretty scary application of these ideas. Okay, so just going back, thinking about the map, this is all about sensitivity. We're making perturbations to the input and they're making changes to the output. And if you follow that literature, you'll find that there's a war going on between people developing algorithms to create these examples and other people then trying to develop algorithms which will either spot that these attacks are being made or try to train the network in a way that is more robust to these types of attack. So the attack and the defense are both upping the ante. The paper at the top here takes a step back and looks at a more interesting, I think, from a maths perspective, more interesting, bigger picture question, and just asks, are these adversarial examples inevitable? Are they always going to exist, no matter what you do to try and stop them? And these authors prove some nice results using something called the isoperimetric inequality, which is to do with if you cut a sphere in half, do the epsilon expansion of that boundary, how much of the whole sphere does that contain, the unit sphere, and in very, very high dimensions, you get weird effects kicking in. Some work I did with colleagues at Leicester looks at the similar question. We used a slightly different viewpoint using concentration of measure, which also is to do with somewhat counterintuitive effects which hold in very high dimension. So I'll give a little bit on this topic just to finish off with showing the kinds of things that can be done. So first of all, we have to say what we mean by an adversarial attack. So given a classification tool and given a data point X, say some image, then it admits an epsilon adversarial example. If you can find the perturbation of size no more than epsilon, so you perturb it to y, such that X and Y are classified differently. Okay, if you think about it, we're not saying that the classification map has got it wrong, because we're not trying to say which is the correct classification, and in general we don't know that given new data points. All we're saying here is you get different classifications on 2 points which are very close together. So given X, we can make a little perturbation of size no more than epsilon, which changes the classification of that input data. Now, to prove a result, you have to make some assumptions, and the main one that we need to make for this result is that the data that we're looking at is drawn uniformly at random from a unit radius Euclidean ball. So here's the type of result that we can prove. So under appropriate conditions, which are to do with the classification not being degenerate, then there certainly is a constant k, non-zero, such that something is going to be true with probability at least k. So what is it that's going to be true? It's that if you give me any epsilon, then I can go into sufficiently high dimension, and here the dimension is where the data lives, such that a randomly chosen point will admit an epsilon adversarial example. So if you want very, very small perturbations, I can find a high enough dimension in which a randomly chosen point will be susceptible to an epsilon adversarial example with probability that's non-zero of at least this value k. Okay, so in terms of epsilon, the scaling that we need for this result is roughly 1 over epsilon. The original work I quoted earlier was more like 1 over epsilon squared, so that was a slightly weaker result. But the point is, if you're living in a high enough dimensional space, then a randomly chosen point will be susceptible to one of these adversarial attacks. We also moved on to do a slightly different type of attack, and we call these stealth attacks. And here the idea is that someone hacks into the system and physically changes the neural network. Okay, so given the classification map, and we're thinking of these deep networks here, and given a validation set of m points, and given an epsilon and a delta, a stealth attack is a perturbation to the map. So we change the neural network map F to F with a hat on it, such that on this validation set, nothing really changes. So the network under the perturbation behaves in almost the same way. So it's within epsilon of the original network. But on my specially chosen point, x prime, I've perturbed the map by at least delta. Okay, so imagine I'm applying for medical insurance. I hack in to the firm's network. I want to make sure that that new network still behaves the same on all the data that they're aware of. But when I make my application, I'm x prime. I want to make sure the network gives me medical insurance. So it does whatever I want it to in terms of output on my particular data point. So that's the sense in which we're thinking of a targeted stealth attack. And there are lots of options here for how you might want to perturb the network. So here's the kind of thing that we can prove. So given any epsilon, which is the small amount you want it to differ by on the validation set, and any delta, which is the larger amount you want to change the output by on your new point. If this point is random, then I can pick a parameter kappa in this way, and then I can just add this extra unit, which is essentially adding a neuron. This is a rel-u operator, which is an approximation to the sigmoid function earlier. By adding this extra term into the network, which is like adding a neuron, then I get a stealth attack, according to this definition, with probability at least this much. And remember, n is the number of validation set points I have to satisfy. So as m gets larger, it's harder to do the attack, but in my favor, I've got a 2/3 to the power n. So if the dimension is sufficiently high, then I can make this close to 1. So there will be a stealth attack for a randomly chosen data point. So those are the kinds of results that can be proved. And I think there's lots of interesting maths in here. Some of it is quite analytical, some of it is quite computational. So there's a nice variety of things that can be done in this area. I'll just finish by picking out some of the links with what you may be studying or researching in the maths and stats world. There are opportunities here in terms of training networks, in optimization. There are links with stochastic analysis. In particular, solving stochastic differential equations is closely connected with some of the tools used to perform the optimization. At the heart of all this are big matrices, sometimes with very specific structures or specific sparsity. We can think about susceptibility to perturbations through condition number estimation, backward errors. More generally, from a numerical analysis perspective, we want to understand how low floating point precision might affect things, whether we should be mixing a little bit of low precision with higher precision units where necessary. So where would the best place in terms of efficiency and accuracy be to perform the extra high level arithmetic? Lots of high performance computing issues here. At the heart of the training is the chain rule, and in particular techniques in what we used to call automatic differentiation. So that's a fairly standard field within numerical analysis, which is now essentially one of the key aspects of the training of deep learning networks. I touched just previously on approximation theory, in the sense that a lot of the results you prove rely on high dimension. So things happen if you have a high enough dimension for your data. There are issues there about whether the kind of data we see really does live in high dimension. Although the number of pixels might be large, maybe all the pictures that we see live in a much lower dimension. That would be a great thing to try to quantify. That might allow us to overcome some of these issues, or maybe just to exploit that lower dimension. And of course, there's lots of stuff that can be done with colleagues in other areas. Interdisciplinary work in this field is rife. And there are issues around things like ethics and privacy, interpretability and security that I think as a community, we shouldn't be ignoring. We should be getting involved in these issues and trying to help out with some of these thorny questions. Okay, so I'm happy to finish there and take questions.
Thank you very much, Professor Higham, for a very interesting presentation. There are a few questions by the audience. So a lot of training data sets contain inherent biases. A lot of research is focused on ensuring the accuracy of machine learning algorithm processes. However, little seems to exist on building unbiased data sets with which to train the algorithms on. Given the number of embarrassing results for companies recently, such as Apple's credit card, for instance, should we not be focusing on the biases inherent before even applying these approaches?
Yes, that's a very good question. There is work from the maths perspective on this. As mathematicians, we like to make definitions. In fact, we more or less have to make definitions if we're going to make any progress on the analysis. There are some interesting definitions now of what it means for an algorithm to be, or for the data that you put in to be biased. It's not really my main area, but I've heard talks on this. I think there are interesting questions. In particular, just simple things like anonymizing data. It's a tricky business to try and make data anonymous, and to make algorithms somewhat fair, and even defining what you mean by fair is also tricky. So yeah, that's a very good question. It's not my area, but if you look around, there are mathematical questions there that could be tackled.
Thank you very much. Probably we have time for one more question. Gradient-based and backprop are fundamentally based on calculus. However, it does not seem particularly biologically feasible, given what we do not know about the brain. Is there anything to say about self-organizing mechanisms for learning?
I'm sure there is. I tried to hint at the start that it's a somewhat heuristic connection. It is true that some of the techniques used in deep learning are motivated from biology. For example, the way that images are processed, the types of matrices that are constructed, these convolutional neural networks were motivated apparently by looking at what might be happening when we process images. But I think that connection is somewhat tenuous, and I don't think anybody these days is trying to claim that what neural networks do is really reproducing what happens in the brain. So I think you've got to be a little bit careful about saying that we're doing biology on a computer. I think the best you can say is that we try ideas out, and some of them seem to work, and the ones that seem to work best have some sort of connection to things that we may be doing ourselves.
Excellent. Thank you very much. I'm afraid we don't have time for further questions, but we will try to answer them through the chat board.